Okay, we can start. So we're just going to continue where we left off on Friday. And so just a reminder, the midterm is approaching. It's the week after next, so 2 weeks. So this week's homework, which is out, and next week's homework are going to be the last homeworks that are in scope for the exam. Project information will be released this week also. Okay, so if you remember last time, recall, we talked about RNNs motivated by the learned common filter, right? RNNs as generalizations of a learned common filter. Now notice that once it's learned, it's no longer a common filter. It's just a filter, right? It's a learned filter. So the idea was, remember, that in a learned common filter, you had some equation you wanted to learn for how you update your h's. So I'm going to switch notation a little bit here. H hat t, for example, equaling some weight matrix that relates h hat to h hat across times, t minus 1, plus some weight matrix that relates h hat to inputs, which acts on some input xt. All these are vectors. Okay. And now, in general, you could also, if you think, that there's actually a constant term you need to add here as well that you know about, you can also add that. Some bias term, if you think that one exists. So we said if you have that as your dynamics and you don't know, these are the parameters, to be learned, you can just set up something so that backprop can give you what those are, from sequential data. So we can learn what this is if you had, so last time, recall, we talked about, can learn filter parameters from, so last time we talked about how you could learn it if you believed there was actually ground truth on H, right? So if you have data that's H at time t, X at time t, sequence data, or you could learn it from just xt sequence data. But if you do this, you need to add, you put a loss on predicting next xt, and that involves learning some extra parameters for that prediction, right? The thing that connects the h to the x. Okay, so we talked about that last time. Now, if you thought that back to your case of a learned common filter or learned filter, if you thought that, well, your goal of learning these h's is actually to achieve some other task, right? You want to learn how to get the hidden states from the sequence X, which is what you observe, and your goal is to actually help you do some other task, you could also, set it up Or another case, you could also learn from xt and some other zt, right? Some other linear function of h that you actually care about predicting, right? You could do this as well, right? So for the x, you made a set of parameters to connecting h to x, and if you have some other z that you care about, you can make a set of parameters that connect h to z. Does everyone understand this? Like, this is just now, you can just do backprop on this. It's all good, right? Where you simply have, you take your sequence, extend it through time. So picture, this is dying. Nice. Picture was, you just set up all learn parameters. You have parameter sharing across these. You have your x's coming in. You can initialize at 0 for the hidden state. This is h1 hat. This is x0. I guess, let me look at the time. Oh, so matching my notation, I changed to x1, x2, and so on. Right? That's how your RNN is set up. Now, if you whatever you have in your sequence, you can set your losses up. So if your sequence is you have actual ground truth h's, you can put losses here, 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 here. If you have just x's, you can stay from h1, make a predictor of x1, and so on. Sorry, from 0, make a predictor of x1. Sorry, from here, make a loss, which you cannot do. It won't do anything useful because there will be no gradient, so I'm not going to worry about that. From here, you can make a predictor for loss from make a predictor and make a loss that tries to predict x2 and call this x2 hat and so on. Right? That's how you can learn from talk about this. That's how you learn from this. And if you had another task, some other linear function, you would replace this x2 with z, and this would learn the mapping to z. Right? You could combine that. You could also have a loss on predicting x2 as well as a loss on predicting z. Right? You have lots of choices of how to do that. Okay, so make sure everyone understands this. Everyone understands how this kind of learned common filter thing works. We talked about it last time. And then we said that to generalize to RNNs, we add nonlinearity. Which generically can be done by just replacing this entire linear function block with an MLP. MLP with weights W. New weights. Now, it was all last time, so hopefully this is clear, but I want to make sure that people can ask questions, and I'm going to kind of go into more details today, what's going on. Is everything here so far clear, people? Okay, good. So now, we said last time to get more expressive power, we have two choices. A can increase width and depth of MLP in each box. And a part of width here that I didn't mention last time is including making the hidden state bigger. Like more dimensions in the hidden state. So remember, even if you think about just your canonical example in your mind of the learned common filter, you know that you can have the hidden state to be larger than the size of the input, or it can be smaller than the size of the input. There's no connection between the size of the hidden state and the input. Okay? So it's good to remember that. So the same thing is true in general, right? So it's a hyperparameter for us to choose. That's one approach we can follow. But the other approach is we can compose RNN filters with each other. And that's the approach that we typically do. Right? This is the actual practical approach that people do. People do, a combination, of course, but this is where people put a lot of, most people do. Standard choice. So what does that mean? It means you make your picture like this. So I'll just use the RNN thing with some weight for 1. So this is taking inputs. Weight sharing. Okay, so that's like what you have if you have just an RNN straight. So there's nonlinearity in here, there's an MLP in here, whatever you want. Then to compose these things, what you can do is you can take this hidden state and you can make it the input to another layer. With its own parameters. So you can think of this as a learned filter that then produces a state which is the input to another learned filter. And you can keep doing this. So this particular thing brings up this confusion which occurs in RNNs, is what's a layer? Right? Because you're going both horizontally with kind of the length of the sequence, time sequences, and vertically. So the tradition in RNNs is to call these layers. So this is layer 1, this is layer 2, and so on. You can stack them vertically, and that's like the composition of filters. So you see what's happening here is that we're trying to capture the modeling spirit of layers in convnets. So in convnets, the different layers modeled different filters that are being applied to the input. So we want to keep that. So the different layers here represent different filters that are cascading together. And the fact that you have to go across time is just the fact that your input is sequential. Okay? Backprop, however, it doesn't care what you call things. Backprop has to move through all of this, wherever your losses are. Okay, so is that clear to everybody? Okay, so now we get to the main challenge. Maybe I'll write it over here. So the main challenge in RNNs is long, like, chains to backprop through. Because in addition, so if you have a loss, for example, up here, so there's like, suppose that n, you have a sequence of length 100, and you have, 7 layers, 7 filters composed together, right? Backprop has to flow from that last loss up there, down and through, and all these different paths. Backprop has to go through all these different paths. So you have, these very long chains that you have to backprop through. And what's making them particularly long is actually the fact that you have these sequences that are long. Not necessarily the number of layers you stick on, but that too. Does everyone understand the issue? Okay. So this means that everything so we need to worry about, everything we worried about before, we need to worry about here. We need to worry two things: exploding gradients because that will stop things from working at all. You'll just get, if you have exploding gradients, practically, in the context of an RNN, at iteration 1 or 2, you'll get nans. Okay, you run it, you'll be, let's try it. Let me see what's happening. Let me print out the values. NAN, 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 NAN is what you'll see, which is, like, it doesn't work at all. So you have to solve this problem, otherwise stuff just simply doesn't work. And you also have the problem of dying gradients. So this is required, won't work at all without won't work /train at all if we don't fix this. And dying gradients means that as you're having the gradients go down, what they correspond to is you can't, if you have dying gradients in an RNN, it means you won't be able to learn long-range dependencies. So dying gradients are actually an inductive bias in this case. Won't be able to learn long-range dependencies in the input. So we have to solve these problems. Now you say these are problems we've seen before, and why can't we just solve it using the approaches we already had? And we'll talk about that. Yeah.
That the problems comes from the long chains.
Yeah, these problems come. So the question is, where are these problems? Why do we have to worry about exploding gradients and dying gradients? The reason is that we have these long chains to backprop through. The computer will happily do it. It'll happily algorithmically execute the backprop. That's not the problem. The problem is that whenever we saw that you had depth, you have the problem of the gradients are being passed back and they're being multiplied by numbers as you go. And whenever you have numbers that keep getting multiplied by other numbers, you have the problem that those numbers can explode or go away. And this is a problem in ConvNets too. except in ComNest, we didn't necessarily have to deal with very long sequences. But in RNNs, we have no choice but to deal with very long sequences because that's what our data is like. So we have to deal with this problem. Now, I'm going to talk about using the same things that we used before, which is good for you to think that will those still work. But I wanted to introduce one more ingredient that's used in the context of RNNs. So I'll call it quote new, because it's not really new in history, but it's new from the perspective of how we're treating it in the class. New ingredient. One of the new ingredients that's used is to say maybe we can actually choose our activation function to help deal with the problem of exploding gradients. So I'll call these saturating activation functions. Nonlinearities. So first, I'll just draw the classic examples that are used, and then I'll talk about why they're useful. Then I'll comment a little bit on the history here. So the example of this, so all through now, we've always talked about nonlinearities. Our default has been ReLU, and like this modification, like the Gaussian ReLU, and both of those. So instead of like ReLU, which looks like this, and its variants, which all look like this, we can use things that like tan H. So what does tan H look like? So forgive my drawing of tan H. Won't be the most accurate drawing of tan H. So this is hyperbolic tangent. Looks like that. So these are called saturating nonlinearities because if you feed a big value in, it doesn't keep getting big. It kind of starts saturating. Okay? Whereas ReLU, if you feed a big value in, will give you a big value out. So there's tan H and like sigmoid in particular. Just saturate different places. So if you think about using these nonlinearities, they have the property that they apply their own brakes on the gradients, right? Because the derivative of the ReLU is 1 out here. Here it's 0, it just kills everything, but over here it's 1. Which means that this ReLUs encourage the multiplications to go back and keep, whatever the weights are, just keep multiplying. For tan H, if say the weights get big, right? If the weight gets big, you're going to spend more time on the tan H out here. But then here, the derivative is very small. So that means that, the gradients will also be small, which means you won't be using, you won't keep getting bigger and bigger and bigger. Like there's something like acting as a brake on the weights themselves. Do you see that? And the same thing is true for sigmoid for the same reason. It's a saturating nonlinearity. The derivatives will go to 0, and so it won't let you get too big. Yeah. Yeah. So I was going to comment on this. You can also, so traditionally, you have many things you can use to solve the problem. So gradient clipping is another thing that is around for all kind of architectures. And so, of course, you can also use gradient clipping. And we'll talk about the others. So yeah, gradient clipping is also something that can be used. Historically, for RNNs, people have liked to use tanh and sigmoids. Actually, originally, like I think I mentioned this before, in the sort of golden age of neural nets that was in the 1980s, and a little bit in through the early 90s, they would always use tanh and sigmoids all the time for everything. They didn't really use ReLUs, even though conceptually for us now, ReLUs are way easier to think about and implement. So historically, RNNs have used tanh and sigmoids in certain places. Gradient clipping is a standard tool that can be used with ReLUs and so on that will stop the gradients from exploding, but you'll still get, so if you just do clipping, for example, here, yeah, so clipping is used as a way to stop things from going crazy. Clipping, however, does distort the shape of which direction you're moving. And so people are more wary of clipping as something to use, it's kind of a last resort type of thing. Not to say it isn't used; it's used all the time, but it's makes people more nervous than changing the nonlinearities. So a little more comment here. If you think about what these are generalizations of, right? It's a generalization of a learned Kalman filter. So a learned Kalman filter is fundamentally about learning some kind of dynamics. And Kalman filter is learning linear dynamics. Now, linear dynamics, has the property, linear dynamics will, it has only a certain set of behaviors it can do. Linear dynamics can explode exponentially, it can explode out in a spiral, or it can go in a circle, or some kind of ellipse type shape, or it can go spiraling in, or it can go kind of exponentially down. That's kind of it for linear dynamics, for what you would do if you don't have something driving it, right? You don't have any other choices of what linear dynamics can do. Nonlinear dynamics have a lot more interesting things they can do. So nonlinear dynamics can have, also limit cycles, where things will spiral in to a circle. Linear dynamics can only spiral into the origin, but nonlinear dynamics can spiral into a circle. Nonlinear dynamics can also have chaotic behavior, where all kinds of weird things happen. Now, one of the things that people believe about physical systems is that physical things in the real world cannot run off to infinity. Okay? Does everyone kind of very intuitive? Like you can't just blow up and go off to infinity. It doesn't happen. Some kind of nonlinearity will kick in and prevent you from running off to infinity. And so there is a belief in kind of originally in the modeling of RNNs, if you're modeling some kind of nonlinear differential equation underneath, right, is what you're trying to capture, thing you're trying to learn, the underlying pattern. Remember, these are patterns of sequences. So the belief is maybe the sequence comes from some underlying nonlinear differential equation. Odds are its behavior is not going to run off to infinity. And so these nonlinearities kind of have the property of not running off to infinity. So you built into them. Okay, so that's kind of one of the reasons why people, in the context of RNNs, use those things. Okay, so this is the one new ingredient. Let's talk about more ingredients now. That we can use, standard ingredients. So recall standard approaches. And we'll talk about which ones of those, have some difficulty or which ones are straightforward. So we already mentioned gradient clipping. Go ahead, that's fine. You can easily implement it, not a problem. You can also use normalizations. But when we think about normalizations, you have to be a little bit careful. Okay? So if you think about normalizations, what you might want to do is to say, let's introduce a normalization of some kind. Like, how would you do it? Okay. So if you look at this grid picture, right, where information is flowing both up and sideways, you want to think about, can you introduce the normalization, kind of horizontally and vertically, like what your limits are for what you can do. So you can imagine putting in a normalization. First thing you might think about is if you think about the sequence itself as being the counterpart of an image. Okay, the sequence is the counterpart of the image. Just as we thought about graphs, right? So the entire graph is the counterpart of the image. The sequence is the kind of values on the graph. The graph is linear here. You can think about this as the counterpart of the image. You could imagine putting a normalization here. Does everyone see that? That's something you could imagine doing, is putting a normalization there. If you can't imagine this, like, please raise your hand and tell me, like, so I can talk about why you might imagine doing this. Okay. This is the counterpart of putting in like a layer norm or potentially batch norm between two convolutional layers. Okay? So if you imagine putting a normalization here, you think, okay, like, does anything go wrong? To ask yourself, does anything go wrong? Like, will something stop you from doing that? And will it stop you? When will it stop you? How will it affect you? Anyone want to kind of venture? So what would a standard kind of like, don't use your brain very much, apply a normalization of the same type as you would have for a layer norm, in a standard convnet, stick a layer norm here, what would happen? Like, what would it do? Someone just tell me what it does. Like, just blindly. So if you asked you on the exam, you want to blindly apply a layer norm from here to here, across here, like, what would it do? One of you at least knows at least some of you know. Maybe it's like it's too obvious. So raise your hand if you know, like, what something you could do. Some of you, raise your hand if you don't know. It's fine if you don't know. Okay, like, remember, right now, my objective is not to say, tell me something that works. My objective is simply to say, do you know what layer norm is? Right? And how would you apply the idea of layer norm here, treating the entire sequence as the analogy of an image? Okay, so, yeah.
We might normalize like across each.
So we think about H1. So you have H1, you have H's at layer 1 that are coming. So H1, H2, H3, and so on, going out. And so in this picture, if you think about the classic layer norm picture, this box, batches, channels, and this is an image. This is height, width, these are pixels in an image. So if you think of this as the analogy of an image, the pixels become sequence positions, right? And now for a classic layer norm, what you normalize is across this box. You average across this box. A single, you don't go across batches. You stick in one batch. But you average across the channels and across the sequence positions. Okay, so that's what you would do. You could imagine here, so what you were bringing up right, is a kind of, I think it's called instance norm, right, where you could instead just average across a particular channel, but just go across positions in the sequence. Okay? Yeah.
I guess my question is like, are we crossing this like one?
Okay, good. So now we're bringing up some of the challenge, right? So at training time, right, for training, you could put in a layer norm layer and actually go across the entire sequence as long as you were kind of going from this level to this level, because the processing you need to do is sequential this way, right? But you could just say, okay, I'm going to process sequentially this way, then I kind of like raster scan up, right? Go, right? So you go this way, then you go layer norm, then this way, and then layer norm. So from the perspective of training, if you did it this way, right, sticking a layer norm in vertically, you're free to actually go across the sequence, okay, at training time. The challenge becomes, how do you then translate? So remember in batch norm, if you remember in batch norm, you had the issue of, well, you could apply it during training, you have batches. But then you have the issue of what do you do at test time when you don't have batches, you just have a single image. You face a counterpart of that problem here, is that at training time, you have sequences. But at test time, you might be wanting to execute this thing one sample at a time. Right? Because you're tracking something that's happening in real time, and you would like to generate a particular output. So that's a little bit application oriented. Right? What are you actually going to be doing with your sequences at test time? Does everyone see? If what you're going to be doing with your sequences is going to process an entire sequence all at once at test time, then there's no problem in doing layer norm type things at training time. No complication. If, however, you're going to be processing your sequences one at a time, then you do the same kinds of things you did for making batch norm work at runtime or at test time, as what you have to do the same kind of thing here. Think about how do you substitute the effect of all the other points in the sequence which you haven't seen yet, on average, to come up with a particular value of the normalization. Okay, so the important thing I want to point out is normalizations is subtle, right? You need to think about application and what happens at test time. Also, what everything might mean. Okay, so any questions on like the basic challenge with normalizations? So we talked about one of them, right? So if I tried to put a layer norm in here. Now, there is something you could do, right? You could say, hey, I'm going to put a mini layer norm. Just this big. All I'm going to do is I'm going to make sure that before I pass my activations from this H1 up to the next layer, I'll make them sit on a sphere. Do you see that? Or a shifted sphere. If you do that, that's fine. You can do that at test time. It's all good. Okay? That will stop things from exploding kind of in this direction. Right? Because it's just forcing them onto a sphere every time. But you better have, if you're going to be start putting things onto spheres or ellipsoids or whatever shape you want, then it better be high enough dimensional for this to make sense. Like your hidden state has to be big enough for that to not be a pretty serious distortion. Okay, now we've talked about horizontal. You can also think about vertical. Okay, so vertical, you could imagine putting something in small, like right here. Same thing, putting things onto a sphere. Or if you want, an ellipsoid. Right? So when I say sphere or ellipsoid, I mean like whether you want to have learnable values for the mean and the individual covariances on the individual axes. Right? You can do that. This is fine. Again, no problem. I've never heard of anyone doing this. Okay? Although it's not a problem, right, in terms of doing it, right? But it's kind of very strange, kind of in terms of our intuition, because we're now mixing the filters together in the normalization on this vertical way. Like, but again, there's nothing problematic with this sequentially in terms of doing it. So this is like variations of layer norm. Can do layer norm variations. Batch norm is a lot harder to do. Because in batch norm, you have to deal with the problem of your sequences being potentially, your input sequences potentially being different lengths. And so the batch norm becomes very tricky in how you do it. There are papers on how to do batch norm. So it's subtle just for layer norm, right? Harder, but possible. To do batch norm. So figuring out layer norm variations, you can just do fiddling around yourself. Figuring out batch norm variations is a lot harder. You have to read the papers. But the important thing is you can actually do some of these normalizations. And they will work in the sense of helping you protect against exploding gradients the same way that they work generally. And they also had some effect in combating dying gradients too. Yeah.
How do we interpret like the weight? Like in a covenant, like depending on the length it'll learn.
Oh yeah. So the question is, can you interpret the learned weights in a RNN? And the answer is you can interpret them the same way that you can interpret the learned weights in a convnet. So the learned weights in the first layer are kind of processing the input sequence kind of at the closest level, and then higher up. The difference is that, and we'll talk more about this, in a convnet, we often have the downsampling steps of stride or using pooling. Those kind of things aren't done as often in RNNs, although you can imagine doing them in RNNs too. So straightforwardly, you can do downsampling in an RNN by doing max pool or stride, the counterpart of stride. So what would that be? It would be that instead of having, quote, time tick at the same rate here as here, you could say, well, I'll take two of these H's, and then they'll go into one input of the filter, and time will tick half the speed up here. So in that sense, you can do all those convnet things in an RNN. The challenge is actually when it comes to interpreting these things in the context of the kinds of problems that people like to use or used to like to use RNNs on, which are often driven, a lot of sequential data was actually driven from some fundamentally linguistic process, as opposed to, in terms of practical problems, as opposed to coming from something that was more natural as a differential equation in the world. And a lot of things actually come from that. So for that, this kind of downsampling by stride and pooling wasn't as effective. And so you kind of had this problem of interpretation. The other problem is that when you think about applying this to sequential data that is linguistic in nature, it's very hard to interpret the filters. You can have a filter. It's a learned filter. But what the heck does that mean? Right? It's way weirder. And so people have, it's harder to interpret for that reason. It's not like a blur, right? Whereas in a convet, everything is a variant of a blur or a sharpening of some kind. Yeah, great question. Okay, so standard approaches, can be done for fighting the problem of exploding gradients. So now let's talk about dying gradients. So for dying gradients, your basic approach that we learned, right, was kind of residual / skip connections. So I'll come back to this picture. So if we think about residual, I'll redraw it because it's getting crowded over there. So okay, so we have a picture that looks like this. When we think about residual skip connections, you have to ask the same question. Do we add them, like, what does it mean to add them vertically? And what does it mean to add them horizontally? Okay? Always two choices. The gradients are passing both directions, right? So let's first think about vertical. So vertically, it would mean that we say, hey, we're going to enforce that the hidden states are the same size for some stack of these filters. And I'm just going to add a connection that goes like this, up. Or that would be a skip connection. Okay? And what that skip connection would do is would allow the gradients, right, to sort of flow downward through these skips all the way down. So all the layers would feel the gradient. Does everyone see that? Okay. So vertically, is there any challenge at all in adding a skip connection? The answer is no, right? Can do this. No problem. Just as you do in a ResNet. You can add skip connections, residual connections. Now, of course, if you do that, you're going to want to make the same thing that was true in a ResNet. You're going to want to make this W have a little bit more interesting things in it than just having maybe like the output of this, the nonlinearity. Right? You probably want to add a little bit more stuff, but you don't have to. It'll still work in terms of it won't break anything. Horizontally is more tricky. So horizontally, adding a skip connection, okay, let me draw it here. So adding a skip connection would be saying, instead of just having this feed into here, and then out comes the output, you would add a skip that goes like that. So at first glance, when it comes to just the basic operation of the RNN, like can you compute gradients? Will this actually stop the problem of dying gradients? That kind of thing. Again, there's no problem. Nothing will break from PyTorch's point of view if you do this. The challenge is actually that this changes the inductive bias. Challenging. Impact on inductive bias. Okay, so why does it change the inductive bias? The reason is that there are inputs coming in here. And the fact that you have these inputs coming in here, presumably, you want to depend on these inputs. And like we said at the beginning, sometimes it's actually important for the problem that things should depend somewhat locally on what's going on. So the inputs that are happening right here should be quite important. But these skips are weakening the effect of the local input on what's happening. So adding these horizontal skips would basically make it less favoring of local information, where local means nearby in time, in sequence position. Because what it does is it allows the gradient from the end to flow back. And so, yeah. Why is it a bad thing? Yeah, that's a good question. Why is it a bad thing? And the answer is it depends on what you're trying to do, right? If what you want to do is to learn something which has a lot of dependence on local things, this will make that dependence weaker, will make the inductive bias towards that much weaker. And to overcome that weakening of the inductive bias, you would presumably need a lot more data to say, hey, no, you really need to look at the thing locally, instead of just happening to go back to a gradient, going back to somewhere back there, or in terms of how the gradients are flowing. So, but there are other applications where you might think, oh, I want to actually look kind of globally at what's happening over the entire sequence. Right? Now, what happened is that in many, many actual problems of interest, it turned out that you actually wanted both, right? You want, in many actual problems of interest, especially problems that are coming out of linguistics, like language data, you wanted both long-term dependence and short-term dependence. And this became, if you look at it this perspective, is like a weird balancing act. How can you get both? Okay, so challenging. So now, how can you get both? That's the real trick. Does everyone see the fact that this is more challenging? Okay, so I'm going to talk a little bit about what you actually want. And here, then, I'm going to disclaim some topics from the exam. Okay, so what do I want to say? Challenge to using RNNs many problems. Right? Challenges, we have multi-scale information. We can have a context, I'll call it a context, that is long-lived. In the sequence. Long-lived, I mean in the sequence. It lasts for a while in the sequence. But the problem is, it can be long-lived, but can shift suddenly. So examples in linguistic data is your sentence ended, another sentence began. So the context changed for understanding with local information, right? You're in a new sentence now. Yeah.
Is this the motivation why we like
Yes. So great question, and I'm building towards it. Is this one of the motivations for thinking about attention? And the answer is yes. Yes, it is, and I'll build up to it. Historically, the challenge was this particular challenge was solved or attempted to be solved by using something called LSTMs, which I'll talk about. But I'm going to just tell you now that I'm going to disclaim LSTM details from the scope for exams. Right? We're going to give you homework that lets you, play with them, but we're going to take them out of scope for the exam. And one of the reasons I'm going to take them out of scope for the exam is it's really hard to ask a non-tricky question about LSTMs. And when you ask a tricky question, for many of us, we see that we think what the answer is, then we say, let's just try it in PyTorch, and half the time we're wrong. So that's kind of unfair to ask you, right? Because you won't have PyTorch to see what works and what doesn't work. They're really subtle and delicate in terms of what works and what doesn't work. Also, we can excuse this to ourselves because practically speaking, in many problem domains, LSTMs have been supplanted by what we'll talk about next, which is called transformer architectures based on attention. So we feel less bad about taking them a little bit more out of scope for the class. But you should know what the underlying engineering tension is, which is why I'm talking about it now. Okay? So the problem is you have context that can be long-lived but can shift suddenly. And second, you also have details that are relevant, that keep evolving. Evolving / mixing, right, with time. Now, I want to comment on something here, right? It is a completely natural reaction that you should have to say that this issue is not unique to sequential data. In fact, you can say that in images, you have the same problem. Images also have things that are local and then change in an image, right? You can have, same thing happens there. And you can also have details that are like local. And so since you asked about, is this related to attention? In the context of an image, the way that these kinds of issues were addressed before the advent of transformer architectures, and to some extent is still a very important thing to think about, is you have this UNet approach that we talked about. If you care about doing something at the level of individual pixels, you have the UNet approach where you have some kind of downsampling that's capturing the context that you expect to be global, again at different scales in the UNet. And then you have the details are still accessible to what you're doing. Okay? The UNet approach, as we'll talk about later, is intimately connected to the motivation for doing attention, right, in the context of sequential data. You can think about it as one way to do that is to say, how can I get the same kind of thing I had from a UNet in the context of a sequential problem? Okay, and that leads you to attention. But there's many different ways to get there. That's one of the ways that you should think about. But you have this problem. So again, people can try to deal with this problem by saying, hey, maybe I want to have this very long-lived context simply achieved the same way I do for images by having lots of layers, do downsampling, and have something which is local but very slow in terms of sequence blocks, right? That's keeping track of this global state. And then you have to figure out, okay, that's nice, good to know. But if all the processing is happening here, how do you bring that down for the lower ones to take advantage of? Right? So you could try to do kind of UNet-y things to do that. But those approaches tended not to work, in part because although for images, for some reason, initially, people got very good results without thinking about the fact that where you get these sudden shifts varies image by image. in sequential data, especially sequentialist is linguistic, these sudden shifts are more sudden and kind of break those kind of approaches, practically speaking. Does everyone understand the challenge, kind of conceptually? So you have this problem. You want to solve the problem of dying gradients, but dying gradients aren't fully a problem because they are biased towards learning things that are local. So you want to solve the problem of dying gradients while still keeping some gradients dying. So it's weird, right? Contradictory things that you want. So what happened historically is that people came up with, let me see, where do I put it? Kind of got myself into a corner. Okay, remember that corner. I need more space. Maybe I'll just use this part. Key idea. Behind LSTM. Also, GRUs. So these are gated recurrent units. LSTM stands for long short-term memory. So the idea is, if you want, the meta idea is, if you want two contradictory things at once, what you do is you offer the network both choices and tell it to learn what to do. Okay? Learnable. How far back the gradient should flow. Right, in a way that depends on the instance. Instance here is instance of sequence. Everything is sequence data. So how do you do this? So basically, you want something that looks like a skip connection, right? That can be gated off. So it's a skip that's sometimes there and sometimes not. So how do you make something be that way? So the key idea is something called a forget gate. So you have a context, and you multiply it by something, which is a forgetting function. And this thing should be something that's like between 0 and 1, and usually 1. It's kind of confusing because it's called a forget gate, so I'm going to use the standard terminology, but f of being 1 doesn't mean forget, it means remember. Sorry. It is what it is. Okay? And then, this is a learnable thing. This is learnable. And then, you add to it something which gets multiplied by 1 minus f, and another input, which is learnable. So if you look at this structure here, what this structure does is it says that CT plus 1 is, if this is usually 1, it's basically usually just CT. Right? So this is like the skip that's actually happening. So in that case, the gradient will flow straight back through here. But if this f goes to 0, then the gradient going back here will block. Why? Because if f is close to 0, then how much does a small change here depend on this? The answer is very little, because this thing's being multiplied by something close to 0. So this is like a controllable gate for having the gradient go back or not. So you can use this in place of skips. That's the idea. However, the details of this can get involved. So first I'll describe some basic details. If you want to have something that's between 0 and 1, what do? How can you get that structurally? Well, you can use the sigmoid. So f is usually the output of a sigmoid. Stuff. Okay? What's the stuff inside here? Well, and this is where life gets really fun, right? If you try to read these papers and look at the code. Okay? So if you look at the sigmoid, what can it be a sigmoid of? Well, what do we typically have, right? You have some weight acting on the input plus some weight acting on the hidden state, plus you can imagine some weight that acts on this context state, right? Plus a bias term. That would be the standard approach. Great fun. If you read the paper says this, okay? The code drops this. Okay? So, yeah, question. So the idea is this is like acting like the skip. So the standard H is still present. What we're doing is we're replacing this in spirit with something. Some path for the gradient to go by. So we still have this, right? But we want to add something for the speed the gradient going back. So we make this. Okay, does that answer your question? Yeah, sorry, I kind of painted myself into a corner. Okay. Input is, similar. So this can be tan H, same stuff. Okay? Now, the question is, conceptually, if you do it this way, and you keep dropping, so there's a couple of things to think about. Why is it that you actually end up dropping this context from these functions? Okay, this is really weird. All generality would tell you, hey, you should depend on everything you have access to, which is you should depend on the X, the H, you should have a bias, and you should depend on the C, because after all, C is carrying information. But the problem is, if you depend on C, there will be a gradient asking C to change. But gradients asking C to change will make this thing want to forget, so that C can change. But you're trying to have C be stable and steady. So you don't want to have too many things putting gradients on C. Okay? But this becomes where the delicate balance becomes really weird and the black art, basically. So you often drop the C's from these functions. But then you have a problem. There has to be some gradient on C, because you have to have some way of learning that you should forget something. Does everyone see that? Right? You can't have everything not depend on C, because then what's the point of having it? And so what people do is they add an interesting dependence. They say the final H that you emit it's going to be some O, whatever you have before, component-wise multiplied by the tan H of C. So that there's some dependence on C, but not too much. But if you can imagine, this is pretty, like, I'm describing to you the story. You can read the paper on LSTMs, and you can look at the code, and you can see in LSTM and GRU papers. So GRU is like a simplified version of this. I'm describing you in the spirit of GRUs, actually. The actual LSTM paper is more complicated. It's very delicate to get this to work, and this delicacy is not as well understood theoretically or conceptually, is more an empirical thing. People figure it out. If I do this, I will be able to learn just right kind of dependencies for certain application domains. So we're not going to ask you exam questions on this. There's code for you to use, that play with, that will let you do it. There's a question of when do you use an LSTM? The answer is that as of right now, our best indication for practical use of LSTMs is use them when you can't use a transformer architecture for that problem, or transformer architectures don't work. So why would that be? It would be, and we talk about transformers more, but if we're talking about LSTMs now, I should just mention it to you. Transformer architectures tend to be a lot more data hungry in training data that they want. So if you find yourself in a situation where you feel like you're bottlenecked by relevant training data, and you still have sequential issues for which you need to deal with sequences, then you might want to consider using LSTMs for your problem, because they might be able to work, and you can't get your transformers to train. Okay? But otherwise, you probably want to be using transformer architecture for sequential problems that you face, for which a straight RNN won't work. Okay? So I just want to mention this, talk about it, because it is important to know, and it's useful to think about how you kind of reason about the engineering, but it's a little too tricky to ask on an exam. Okay. Any questions on this stuff before then I'll start into kind of how do you use these kinds of recurrent models in the context of sequences and different kinds of problems? Yeah. Yeah, so it's kind of, it's really tricky, right? So what's actually happening here, so I'm gonna like push this aside, is you have a box. So before we had H, some learnable weights, H would go in and H would come out, right? And now you also have C. Context comes in and context comes out. The H depends weakly on, right? On the C. There's a product, this thing. Okay? Sorry. Tan H. Okay, so that's what's happening. Now, there's still a question of what gets passed up. So that goes in the next box, right? Which has similar weights associated with weight sharing across it. So this is like an LSTM cell or a GRU cell, right? They kind of go this way. When you pass something up, you do not pass C. You only pass H. Again, the reason is you don't want to have a gradient on C that's asking it to change, unless you absolutely need it. So that's the way you put these things together. You stack them up. So this is one layer of a filter that's built off of GRUs or LSTMs. And then you pass the hidden state up to W. Of course, there's actually a second hidden state which you do not pass up. Any other questions on this? Yeah, you had a question? The question was, is there like a rule of thumb for when you should use a transformer versus LSTM for a sequential type problem? It's empirical, right? So again, okay, what will be the recommendation? The recommendation is see if someone else has done it using a transformer. If the answer is yes, and it seemed to work or something close, then probably just use a transformer and fiddle with that. If you find that it doesn't work for you, ask yourself, is this a problem where you think you don't have enough data? If the answer is yes, I do not have enough data, you feel you don't have enough data, then you say, maybe I should try a transformer. Or instead of a transformer, maybe I should try an LSTM style approach to this problem and see if I can get it to work. Again, go look at papers that might be using LSTMs for similar type problems. If you can find them, build off of that and see which one works better for you given the data that you have. That will be the kind of recipe here. Default to trying a transformer first for sequential problems today, but you might need to fall back to this. Yeah.
The GRU stuff for affecting the gradient vanishing.
So both the LSTMs and the GRU, both of these are trying to deal with the fact of the dying vanishing gradients across the sequence by creating a path that's like a skip connection path, but that's gated, so that it doesn't prevent you from learning the dependency that's very local. Whereas it's too strongly inductively bias you away from that. I haven't seen anyone, for example, do the analysis of like doing an RNN and just putting the skips straight in, like without the gating, against the data requirements of a transformer. I believe it's probably would not perform as well, as the transformer would be more data efficient, but I've not seen people work it out because it's kind of that kind of architectural choice is kind of lost in the mist of history, you know, for people's discussion of it. People just think of LSTMs as the better thing. Actually, yeah, as a general rule, you should be wary of consensus always that something is better. Things are better in context. And you need to understand where things come from to understand, you know, what else you might do. But still, the general rule still applies, practically speaking. You know, do what other people do. Okay, so I wanted to spend a little bit more time of thinking about, okay, we built this like technology of RNNs. How do you use it for actual problems? So I have a little bit of time, so I'm going to spend it. So for problems of sequences, there's many, many different kinds of sequence problems that you can have. And you need to think about how to build the neural architecture to deal with the specific kind of sequence problem that you have. So I'll start with one example so we start off with things like filtering, right? So filtering style problems look like this. We have inputs, input sequence, and you want an output sequence, right? In real time. Okay? The common filter is like this. The output has to be available to you soon after the input. You can't look ahead. There's no look ahead allowed. This is one kind of problem. It's the problem that motivated the construction of the entire architecture. So it's there. Now, there's a particular variant of this problem that is interesting, which is a variant of this problem is problems of generation, when you want to generate a sequence. Your output is a sequence that you have to generate. Variation. So when you're generating a sequence, what you need to do is to have the input include the outputs you've already done. Okay? So for example, if you're trying to generate an utterance, what you've already said matters to what you say next. So this is sometimes called autoregressive use of a network, right? Which means you just take the output and you feed it in as part of the input for the next time step. You might have other inputs too. Okay? Does everyone understand how that's a kind of real-time problem? Because when you're generating a sequence, you can't say, let me wait to see what I generate 4 words later. Right? You have to say something now. And then you'll say something next. And then something next. And then something next. And then there'll be 4 words later. Right? You can't look ahead to what you will say. You can plan. You can keep it in your internal state, what you might say in the future. But you can't actually look at your output later. Everyone clear on that? Okay. So, well, time's up. One of the things you'll do in discussion is you'll talk about something, and you'll see on the homework, is some things that you have to sometimes do to have your generation work, give you better generations. Because sometimes what will happen is you're going to think about the outputting as, so we normally think about these kinds of problems from a common filtering type problem as a regression style problem. You're predicting real numbers. But we know in the context of discrete objects, you often want to think about classification style. So sometimes the outputs you have naturally from your network are probabilities. They say, what's the probability, or what's the kind of score of generating the following thing? In that case, sometimes you want to take advantage of those scores and basically allow yourself to backtrack and say, oops, I painted myself into a corner like I just did, right? When I kind of ran out of board space, right? And that's what you'll talk about a little bit in discussion as well. And it's on the home. I think it's on the homework, or will be on the next homework. Okay? So I have office hours now. Again, any questions on the board we'll take now, and then we'll move over to 258.